But what I want to do now is a little bit more hands-on. This will be a little bit more free-flowing. Hopefully it all works and I don't make a fool of myself. But kind of trying to delve into the toolbox and kind of show you some of the features and show you some of the stuff and how you actually implement some things. So, and I will, I need to polish off. I basically pasted a bunch of this is what I want to show people without much explanation that I'm going to walk through, but I'll try to make this into a little bit better demo and we'll put this on the web. And as I said, actually, the NIRS toolbox has a ton of demos already in it that show you how to do various things. And actually, maybe I'll start with that. So the demos, where is my toolbox? So if you download the NIRS toolbox, excuse me, it downloads this folder. Inside of this folder, the plus NIRS, plus EEG, those are all the folders where the files actually are to do the guts of the program, the MATLAB code. Inside of this folder called demos, there actually is quite a number of example demo scripts. So, where's my laser pointer? So if you're just starting to look, this one that's covered up by my mouse cursor here that's called NIRS analysis demo, that's probably the one to start with. That one shows all the basics and kind of the stuff that I'm about to show here with the toolbox. Most of those slides that I presented right before lunch were actually basically screen grabs from that toolbox, or that demo there. NIRS analysis demo, but that one goes through how do you load data, how do you look at the stimulus information, how do you change things like demographics, and then run a first and second level statistical model to look at your brain activity. The analysis demo number 2 goes through a couple of more advanced things like region of interest analysis and so on. I'm going to show some of that. We have a connectivity demo that shows you how to do things like resting state connectivity, hyperscanning, both at the single subject and the group level. With the hyperscanning is what Thomas talked about yesterday, this growingly popular method of basically putting NIRS caps on 2 subjects at the same time, looking at their interactions, and I'm talking and you're listening, so my Wernicke's correlates with your Broca's. Those types of experiments, and we're seeing more and more of those. What's nice about the NIRx data collection and format is when you go through, there was actually like a checkbox to set up your montage to be hyperscanning, to do 2-person scans. And that information actually gets propagated into my toolbox. So a lot of the hyperscanning modalities, you can just read in your NIRS data, NIRx data directly, and it runs the hyperscanning on it with those modules. You don't have to do anything special. There is a demo script here called Homer 2 demo that goes through actually the exact same example data files that are in the Homer 2 package and kind of shows how to do the exact same thing, how to import old Homer 2 data into the toolbox so you don't have to recollect everything. You can use all your old data, and how to actually go through and modify it to do the same analysis within my toolbox. Image recon shows how to do image recon. The forward model and actually downloads, there's a set of data that gets downloaded and it will run through the image recon stuff. There's a demo for generating forward models. This is a little bit more advanced, but it's basically how do you run that Monte Carlo or finite element type models? How do you import structural MRI and run it through? Registration demo, if you look at that, that's a how to do the probe registration. So as I said, with the NIRx data, because you do it at the time that you set up your montages, it has all that 3D. So there's actually no need to, this registration demo only applies if you're not having a NIRx system, because everything that's in that is already taken care of with the NIRx data. But it's basically how do you register up your probe to a 3D atlas or something of that nature. It also goes through then, and there's something I'll show when I actually pull up MATLAB here, of how do you actually use that 3D information to say, I want to do a region of interest defined by the premotor cortex. And so because I'm registered up to an atlas, I can actually do that and automatically detect which channels should be included in that region of interest average. And I'm going to show you that. But that's actually, if you go to this demo, it walks you through step-by-step how to do those kind of things. Code testing demo is, it's kind of a what's called a regression testing on the toolbox, but it basically makes sure that you have the right version of MATLAB and so on, and does some speed tests and stuff like that. And then the compare software demo, this was basically a paper we wrote a while ago that it's the one that commentary on statistical properties that I keep talking about. But one of the things it did in that paper was it went through and it compared the Homer 2 analysis, the NIRS SPM analysis with all the different options of pre-whitening, pre-coloring, and so on, and versus my code, and generated all these figures. And that compare software demo script, if you just open it up and run it, it will actually generate most of the figures that are in that paper. So it lets you kind of test it out for yourself to make sure that you agree with what I did. If you go inside of that demos folder, so any of the files that are in that demos folder are self-contained. You just open it up, press go, it should run without error all the way through. They're all really well documented for trying to follow it. But inside of this examples folder, I started to create a bunch of, these are kind of snippets of code that someone will come up to me, it'd be really nice if we were able to make scatter plots in our ANOVA group level analysis. So I said, yeah, we can do that, and I wrote a script, where is it? Example showing scatter plots from mixed effects, and you need to expand it so you can read the whole thing. But if you click on that button, it'll open up and it'll be the lines of code that you should execute if you want to make a scatter plot looking at brain activity versus age, where you've plotted out all your subjects in a scatter plot. So inside of this examples folder, there's a bunch of additional kind of little pieces of code. Here's one that talks about specifically NIRx, specific data files. Here's one on how to do multimodal EEG NIRS, a little bit of stuff with regions of interest, nonlinear, general linear models, cerebral oxygen metabolism even. Most of this probably isn't even published yet. For better or worse, the toolbox is my working version of what I do. So you saw that my postdoc Frank, when I showed you this morning, he had updated something yesterday afternoon to fix the Granger's causality type stuff. Well, that's because I'm working on that paper right now, and that's code that we're using for that paper. So for better or worse, I've already shared with you that code. So there's a lot of stuff in this toolbox that is, is right at the edge of development. But if you have questions on anything, or you see something you want to know, what did this program actually do, and what is the status of this module? Please, send me an email or something. Yeah.
With range of causality, you're doing connectivity analysis.
We are doing, we've started to move into the multivariate Granger analysis to do the connectivity analysis. It does have, so we have a paper came out this year. And so everything I talked about kind of before lunch with fixing serial correlations and outliers and stuff in the context of the general linear model, it actually turns out that that's even more important if you start to talk about connectivity and so on. And so we have a paper that kind of looked at those, the same, you probably could have done a find replace of the word GLM with connectivity, and all the same arguments about noise and outliers and stuff apply. And we wrote that paper up looking at different connectivity models and wavelet analysis and comparing the different results. That one just came out in JBO. It might not even be on the web yet. I think I might have to approve the editor copy, but it's approved, and I can send it a preprint if you email me.
Is this multimodal or?
That at this point is single. It's like NIRS imaging. We've started to do so. If you start to look at this multimodal analysis, or this Parafac multimodal, which is way more advanced than I want to talk about here, that starts to get in these ideas of multimodal connectivity. Yeah, but you can look at what we've been doing here. if it has been published, please don't steal it, but I'm happy to entertain, because I have more work to do than I have time to actually do it, so I'm happy to delegate, to things.
It's the same situation for us, we don't have enough programmers.
Yeah, that's. So anyway, so this, if you go into this example folders, you can find a lot of things that are, a little bit more advanced topics, but kind of, my titles of these are all pretty self-explanatory. If somebody asks me a really interesting question, I'm like, you know what more people would like to know how to do that, how to generate scatter plots or whatever, I usually put it into this folder. So I'm constantly adding things, and if I write this, my talk here, kind of working through the NIRx data that Thomas collected, I'll probably put it into this examples folder so everyone can see it. Yeah.
Our research group is interested in the NIRs and EEG. So yesterday you mentioned about your data, so that's also part of it.
Yeah. We're actively working on multimodal EEG, fMRI, MEG, and a lot of that is in here.
Thank you.
So if I have time for that, I'll show a little bit of that too. So anyway, so this one here, let's see if I can expand it. This is actually the NIRS analysis demo. This is the one I said to start with. And if you open this up and you just click this run button up here, it'll actually run the whole thing. You don't have to worry about it. But if you scroll through here, it basically, this is what these files look like, and it tries to give some information about what to do to make, to get this to run on your computer. This particular one, at the beginning, it'll actually download a data set from the website. So if you don't have the data, it'll actually download it directly onto your computer so that we have a common starting place for running the analysis. But as I said, kind of based on, one of the things that Toolbox does is based on the load directory, based on the directory structure having groups and subjects and potentially things like sessions, you can actually load that all up and take advantage of that then when you do your multimodal data, or your mixed effects analysis. Okay, so let me switch over really quick to this. So I have a folder, not Rhode Island, we are UTA. So I have a folder on my desktop called NIRx demo. And inside of that folder, I have right now just one subject's worth of data. And inside of that subjects folder, I think there's only one scan of data. So this is data that Thomas collected. I think he's gonna share with you this data file. But it's the same experiment, this finger tapping off-on type block. The NIRx data, it has one folder for every scan. So if you go into that subject one, you'll actually see a folder called scan 1 or whatever the NIRx names it. If you have more scans, you'd have scan 2, scan 3, and so on. So what I'm going to do is I'm going to point my code at that folder here, and load directory. I'm going to give it that folder name, the UTA NIRx demo, and we're going to say you're going to encounter a subfolder, and it's going to denote the subject, and we're going to load that up so the subject name is stored with the file. So if I go and I execute that command, it's going to load up the data, and with NIRx data, it actually saves, when you record the data, it's actually saving that whole 3D head and stuff like that. So when we load up NIRx data, I load everything. So it's going to, you'll see it's going to have that 3D mesh and everything, and we'll have all that registration. It loads it, if you load up, say, if you were loading up 100 files or whatever, it actually only loads that mesh for the first file because it assumes you use the same montage for everything else. There's a way to bypass that if you did, in fact, use different montages. But that loading takes, on my computer, like 30 seconds, so I'm going to bypass that and just go straight to the fact that I already loaded the data before I started talking. Of course, I also wasted 30 seconds explaining that I loaded the data before I started talking. So if you load up the data, raw, I called it raw when I loaded it up. And you see that this data structure, which is, it's an object that my toolbox has created. So this NIRS data is a class of objects that only exists if you load my tool, if you have my toolbox. It's not a MATLAB, it's a custom class. And inside of that custom class, so you've got fields description, which is the name of where that file came from, the data, which is the, in this case, 1800 time points by 40 channels of data, the probe, which I'm going to show in a second, but that's the source detector geometry and explains of those 40 channels of data, which one was source pair number 1, etc. Time is the timestamp on those 1800 data points, and this data was collected at 7.8 hertz. FM is actually for frequency domain NIRS, so FM should always be 0 in this case, but my toolbox does have the ability to handle ISS and frequency domain data, including all that nonlinear, near-fast reconstruction of that. Stimulus, we're gonna play with that in a second, but that stores all the information about the timing when Thomas was tapping his fingers. And then demographics is gonna store, right now it has just the subject name, but that would be the field that we can add things like age or gender or any variable I want, either continuous or categorical. So we're gonna play with this in a second. But as I said, the methods, raw, for example, knows how to draw itself. So if I go and I say raw.draw, and I gave it this entry of 1, I told it I want to draw just the first channel of data. This is now the time course of the data. So you see that there were 2 events called channel 1 and channel 15. That came out of the NIRfast or the NIRstar software, which is basically the left and the right tapping. And you see this time course of signal intensity versus time. And I'll show more some of the graphical type things of how to start managing. You also, so this task, Thomas tapped his fingers for 10 seconds, right? So he's tapping, left hand, right hand, left hand, right hand. But what was stored in the NIRstar data is just this delta function, it's just this onset spike. And there's no information that this was actually 10 seconds long. So if we had set up our E prime or whatever to know that it was on for a block, it would automatically appear as a block. But what we need to do, because that's not how this NIRstim presented the data, we need to modify that right away so that we know this was actually a 10-second block, okay? So let's go and do that. So NIRS.viz, so all of my graphical stuff are in the viz for visible. Didn't really save me space to say viz instead of visible. And we're gonna run the stim utility, given that raw data. We're actually gonna save the data back. So if we run this stimulus utility, it brings up our data file here. If we had more than one data file, we would actually be able to select which data file we're looking at up here, but we only have one, so it's not populated. But it shows us, I have 2 conditions, channel 1 and channel 15. Here was the onset time in seconds, the amplitude, and the duration for each of those conditions. So what we're going to do is, the first thing we're going to do is we're going to rename the stim. So if you right-click on here, you can say rename stim, and Thomas, do you remember channel 115, which is left and right?
That's left.
Yes, 1 is left, right is 15.
Okay, so left, and click on it, rename right. Okay, so we've renamed our stimulus. If we right-click on this field of duration, so we can't enter them one at a time if I really wanted to. If you just right-click on here, I can just set them all because I know they were all 10 seconds long. And then we're going to do the same thing for the other condition. Right-click, set duration, 10. Okay, so this is, so we've now set up, this was actually what Thomas did. He tapped his fingers for 10 seconds. If there was, we can edit. So if I go in and I change the onsets, or I can add extra columns, you can manually edit this. And as soon as I get it working, you can paste Excel stuff into here too. So if you have your timing from E prime or something. As I said, with the toolbox, we wrote it from a command line standpoint. So I do everything on MATLAB command line. I don't use these user interfaces. But realizing that the toolbox was going to be used a lot more if we offered these kind of tools, I've started to write this. So honestly, this was something I wrote about the 2 days before I went to Rhode Island 2 weeks ago for the first NIRx demo. So it still has a little bit of bugs in this, like it doesn't quite import Excel files, stuff like that. But it's working okay for now. We have in this stimulus information, we do have this field amplitude, which is all 1 in this case. What amplitude can be used for is my toolbox allows you to deal with what are called parametric models. So for example, if I had a task that recorded reaction time, and so I have a reaction time, an average reaction time for each one of these events. Or maybe in the case of what Thomas was doing, I recorded I had EMG or something, and I had like the speed or something related to the frequency that he was tapping with. And I wanted to ask the question, what part of the brain covaried or changed according to reaction time or motor speed? What I could do is I can change this amplitude field and put in a variable here that's more meaningful. So I can actually put the reaction times in this field. And what's going to happen when I set up when I start to do the general linear model is I'm going to have additional options that allow me to look at how that amplitude modified the response. So what I would do in that case is I would have 2 regressors. One that's constant, every block is the same height. The second regressor, the height of the block varies with reaction time. So I'm modeling my data as the sum of these 2 conditions. The first one, the one that's constant for all blocks, is going to find brain activity that didn't care about reaction time. So it's going to find brain activity that was the same every time I did it. The other one is going to find brain activity that was changing with reaction time. And so you can enter in this, and actually there's ways to do both linear and nonlinear interactions with the toolbox using that kind of amplitude information. And that's something that in the fMRI community, people are actually reasonably familiar with. SPM, AFNI, FSL all offer that as options. And so a lot of my, again, colleagues from the fMRI fields were coming to me of, why can't I do this with NIRS? And so we had to code it up so that they could. But that's what, if you're wondering what amplitude is, it gives a whole range of being able to design these much more complicated type of experiments that we can look at other factors within this. And Carrie, your stuff you looked at, Carrie, who did her PhD kind of with me, was looking at, she was doing balance stuff, and for each block, the subject scored, they rated how dizzy they were effectively, and we used that as a covariate within this kind of parametric design. So that's just an example of that. But okay, so we've got our stimulus set up. We can go and I click save, and it brought me back, and it actually replaced the raw data there. And now if I say that same raw.draw, I should see my stimulus events with the 10-second duration. So now I'm ready to start running my models. Okay. Let's clear this up for a second. So again, kind of, if you go through the toolbox, it shows you how to do this on the command line. But we do have a GUI, a manager, or a job manager interface. Excuse me, that's really similar to how what Jonathan showed yesterday for the Homer 2 stuff. Unfortunately, I fixed this during Thomas's talk yesterday morning. So I'm sorry I wasn't paying attention for the whole talk because I thought it was important to fix this.
I do believe you still answered questions during that time that you were
Well, I was
working on
coding, yeah.
Can I ask a question?
Yeah.
I was just wondering, like, if you do want to do coding from the command line, I assume you have like all these functions documented, right?
Yeah, they're documented better than the Homer 2 stuff.
Okay.
They're not documented to the point of a software developer would probably slap me for how poorly I am at this stuff. but they're reasonably documented, and the demos are very documented.
Okay, thank you.
So, yeah, so this is the let's see, let's find one that's good. So this this column here is my ever-growing list of modules that we've created. And if you click on any of these, it will actually open up this message down here that tells you all that help information about what it's doing. So this one, for example, the GLM module, this is a wrapper that allows you to run the ordinary least squares, the iterative AR, or the NIRS SBM regression programs. And it talks a little bit about examples within here. If you go, there's a lot of information down here, and if actually you click on this link, it'll actually open up the file, so you can actually see exactly what the file was. But what we can do is, what we would do normally is we can create a pipeline. And searching through all of this, so like the first step in our pipeline might be we go and take the raw data, convert it to optical density. So what we can do is we can select the optical density, we can say add to job, and it moves it over here into our pipeline. Yeah.
I saw import data popped up automatically. Was that automatic?
Yeah, that one was automatic.
Okay.
Yeah. So I'll explain that one in a second, I guess. So over here, what it's doing is it's creating my pipeline. So my pipeline is first going to be import data, run the optical density, and then I had the second job of resample. So it's going to run those all in order. So if I say job.run and I give it the raw data, the data I loaded, is going to run those set of 3 jobs in a row. If you click on some of the jobs, this is why I added the resample, they do have fields that you could edit. So for example, this one, FS, is the sample rate. And so this is going to take whatever the data rate was, 7.8 hertz, and it's going to resample it down to 4 hertz. But if I want to change that, I can go and I can edit in this field and change it. So you can create pipelines and start to stitch things together like this. But fortunately, if you go up here to File, Default Jobs, there's actually a few of these that I've already created that just kind of import and kind of set up the pipeline for you. So single subject GLM, that's the one we're going to run right now. And what that's going to do is it's going to do all the basic pre-processing steps, optical density, Beer-Lambert, and then it's going to run a single subject level general linear model to solve for the stats. The FIR deconvolution GLM does the same thing. It's a subject level GLM, only it sets it up to do the deconvolution version where I'm actually estimating the whole hemodynamic response. Group level GLM is, if you have multiple subjects, it'll actually run the group level model, and I'm going to show that one, just not through this interface. Image Recon sets up a basic pipeline to do image reconstruction, and Write Paper is one I wrote for a joke when I was sitting in the audience at a talk in Michigan a couple months ago that basically goes through and actually makes all the figures and tables and saves them all into Excel of everything that I think you could possibly want for a paper. So if you run that one, it takes a while to run, but you'll end up with multiple folders with all these files that you can just dump right into your anyway, so, yeah.
Yeah, could you please add another model that will automatically save all those tables and figures precisely tables in a text format for?
Yeah, I'll show how to once you go through this, how to save it into SPSS or Excel and stuff for saving.
No, I'm actually suggesting that you also create another model that will save it into text format.
Oh, into LaTeX format. I
work with it. So.
Well, no, actually, the function that uses to save figures, LaTeX actually is one of the options. It's just not one of my default. I think my default is probably EPS,
Yeah,
but I'm pretty sure I can actually do multiple different types.
Yeah.
This a brand new feature that I added like last week in my toolbox is, which I'm actually really proud of, is it outputs to I forget what the format's called, but it's basically, it's a self-contained 3D OpenGL object that you can drag around and spin without anything, and you can actually embed it in PowerPoint, so you can actually have moving brains in your PowerPoint lectures. So, yeah. Anyway, that's just me showing off at this point. Anyway, so this is the job that we're going to run. It's going to first start off with removing any files without stimulus. It's going to this fixed knot of numbers. Some of the systems ended up with, like if they lose data, like it loses data in the transfer saving, it actually stores it in not a number, and so that code basically removes all these not a numbers that cause problems. It doesn't. If you're collecting data on the NIRx system, running that job won't have any effect on your data whatsoever. It doesn't matter. But I always put it in my default pipeline because it also doesn't hurt to run it, and it's just kind of a. But then it's going to resample the data. The default rates, if we open up the job, is going to be that 4 hertz, or 5 hertz in this case. It's going to run the optical density. It's going to run the Beer-Lambert law using a PPF of 0.1. PPF of 0.1 is a differential path length of 6 and a partial volume term of 60, which is kind of the numbers that came out of one of these Gary Strangman papers that looked at what DPF was in simulations and so on. But that's accounting for both, again, that PPF is accounting for both the path length, the fact that it traveled a long distance through the tissue, and that of that path length, only a small fraction was actually spent in the brain. If I get that number wrong, it's just scaling my overall responses, and that number of 5 micromolar hemoglobin change is dependent on that number. But all of my stats, when I do it, because it's going to be divided by it scales both the data and the noise. All my t-scores are unitless, and they don't care about DPF or this PPF term. So it's something to keep in mind when you think about interpreting if these absolute magnitudes of signals make sense, but it doesn't actually end up affecting the statistics. It does have this module called export data that's periodically throughout this. So what it's going to do is when you create this pipeline, when it gets to that step, it's going to save the result, in this case as hemoglobin. So right after finishing the Beer-Lambert law, it's going to run this, it's going to save hemoglobin to the command line, and then keep going. So this just kind of creates a pipeline like that. And at the end, it's going to run this general linear model. And what the general linear model is going to do is, you see the type is this AR-IRLS, which is the autoregressive model that I talked about before the break. The basis set, unfortunately some of these fields you can't edit from this GUI because they're a little bit more complicated. You have to do it from command line. Basis set is one of them. But the basis set is what canonical model am I going to use in my general linear model. So the default is this canonical HRF taken from the AFNI fMRI parameters. But there are other options for gamma functions, for FIR, where you're actually estimating the whole curve. You can actually put it in where you can use a different basis set for oxy versus deoxy, or for condition, in this case, right hand versus left hand, where you can actually impose different shapes if you had reason to believe that they were different. The trend function, by default, it uses just a DC regressor, just a constant, but you can put in polynomials or discrete cosine transforms to try to get rid of a little bit more of the slow drift. Same rules as kind of fMRI. The last one, the go for it flag, is if, in our case, we're not going to have to use this, but if your experiment was not designed properly, such that maybe your stimuli were overlapping too much and you didn't have enough jitter and so on, this can create problems when we try to solve the math. It creates what's called it's just going to create problems when we try to solve that stats. And if you turn the go for it flag on, it'll kind of ignore those warnings and try to do it anyway. But by default, it's off, and so it's gonna tell you if the model was really bad. In this case, the model is perfectly fine, so we don't have to worry about it. So if I hit this run analysis button, it's actually going to run everything. right now. What else? There's also, if there is, you can load and save jobs. So if you have a pipeline that you always like to use, you can load and save it. You can also export the job to a MATLAB script. So what it'll do, it'll actually write a .m MATLAB file, which has all these commands in it, and you can just execute that instead. That feature used to work, but I think it's broken right now, so I'll fix it on the plane on the way home. The other button here, this run regression testing, this is actually kind of cool. This is regression testing. What regression testing is going to do is it's going to take a set of data. You can either enter data yourself, or if you run it through here, it's going to generate it's going to generate data, synthetic data. And it adds to that data a known stimulus on half of the channels, and then runs the pipeline that you just created and reports back what is the efficiency of that pipeline. So it's going to do that same ROC curve to look at false positives, false negatives, the sensitivity analysis. It's going to look at the type 1 control of error, running simulations from the pipeline that you just created here. So right now it's going to run, if I did that, it would run 10 iterations. It'll maybe take 2 minutes or so to run on my computer here. I'm not going to do it, but it'll actually end up reporting on your pipeline. You can use that, say, for example, if you invent a new tool, you put it into the toolbox, or you want to try out one of the Homer 2 tools that we can also import, and you can start to actually compare the performance of the different models or the different types of pipelines. So you can compare, for this type of data, for this type of probe, PCA versus wavelet for motion correction, what is the effect of these two models on performance? And you can actually run that within the code here. Some of the demos actually go through exactly how to do that. So, but we're not going to run that right now. We're just going to close that window. It created the job on the workspace. And so that job looks like this. So it always shows the last part of the job, and then it has this previous job. So the last part was going to export the subject stats to the workspace. Right before it ran the previous job of GLM. If I go and look at this, its previous job was resample, and its previous job was this, and so on. And it chains all the way back. There is a way to look at NIRS.modules pipeline to list of job, where it'll actually show exactly what. And so if you created this pipeline and you want to change the resample function, you can use this and then just go to the fourth entry and change it directly, rather than having to recreate everything. But anyway, so what we're going to do is we're going to say job.run given my raw data. And what that's going to do is that's going to, so you see it's already on the hemoglobin, it already ran the Beer-Lambert law, it was running the stats when it was going dot, 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 it was processing that iterative stats. And so it went and returned, it saved the data as called subject stats, created on the workspace, and now this is what was actually saved in that model. So this, just like the raw data structure, is an object that my toolbox has custom written, and this is where all the stats get stored. So again, kind of same fields. You see the description, the probe design, which I never actually showed you guys. The basis set, it tells you, or the demographics, the basis set, so it tells you what model you used when you ran this. It'll show you the conditions within the file, which are going to be the left and the right. It's got these t-stats, the p-values, and then Q is the false discovery rate, Benjihani-Hochberg corrected p-values. So Q is the fact that in this data file I have 80 comparisons, and this is now the p-value corrected for those 80 comparisons. Okay? What you can do is, if you look, subject stats, so we want to see it first, I guess. So we can say draw. And just like the raw data, draw knows what that means. And so it's going to draw a total of 4 images here. And so this is the color scale here is the t statistic. and did I do this right? HBO on the right side, so we see brain activity on the left. HBR on the left side. I'm sorry, I should flip those two images, but we see brain activity on the right, where we see oxyhemoglobin mirrors where we see deoxyhemoglobin, so oxy's going up, deoxy's going down, exactly like we expect it to. Thomas is a great subject, and we see this brain activity. We can, let's close all. We can, if we give a little bit more commands to that, we can say, I want to show a t-score. I'm going to actually auto-scale it, but I'm going to only show, I'm going to show it at a false discovery rate 0.05. And so now it's going to only draw lines, solid lines that met that statistical threshold. So you see over here, you did have a few channels that were kind of hinting at brain activity here. They're a little bit red, but they didn't meet my statistical threshold. Only the ones in solid met that 0.05 statistical threshold. Okay? We can also do, close all, subject stats. If we say .table, table is another method, and it'll actually spit out a table of all the stats that it solved for. So you can go and there's a way to copy paste this into Excel or save a table as in SPSS form or something. But it tells you, for example, source 1, detector 1, oxyhemoglobin for the left condition. Here is the amplitude of the beta. Here is its standard error. If I ratio those, that's the t-score, which is not significant. In fact, that's a p of 0.07, and even worse if I'm correct for false discoveries. However, I was very powered to see that. So it outputs both the type 1 error estimates here. It also estimates, and I would have to pull up the papers to remind myself on how I actually did it, but it uses what's called a minimum discoverable unit based on the noise structures in the data to actually estimate how powered you were to make this comparison. And so that's the last column. One of the things with NIRS that's actually very different than fMRI is in fMRI, your noise is fairly uniform. No matter which voxel you look at, your noise is all more or less the same. In NIRS, it depends heavily on how well you put the cap on the head. And so regions in, say, the occipital, where you have hair, you have thicker, skull, and so on, you're going to be less powered than other regions. So the fact that when I draw those images and I didn't see brain activity on a particular channel, you don't know necessarily that there wasn't brain activity there. It could have been you just had a really poor measurement and it was just really noisy and you didn't have good coupling. So adding that power estimate lets me kind of starts to look at, and I'm happy to entertain other methods because there's no good solution to this. There's no obvious solution of best way to do this. But we're starting to try to look at this, and you just see some variation like this. I think in general you would find the deoxyhemoglobin are a little less powered than the oxy, although in all cases you're up in the 0.7s, I think the lowest one I see there is 0.65 or so. So you're generally powered with this study. This was a huge change. Finger tapping is a much bigger signal than you would typically get with cognitive tasks and so on. So that does change a bit. All right, let's us start to look at some of the stuff in NIRx specific things. So one of the fields that I've kind of been talking about is this probe. It existed in the raw data. It was then copied over into the. Actually, let me show something else first. I do have a viewer, much like Homer 2. It's called NIRS Viewer. I'm really not creative with my names for things, but NIRS Viewer. At any stage of the analysis, you can run NIRS Viewer, and it kind of gives, just like Homer 2, it gives a graphical interface. You can actually, up here under, under data management, there is ways to edit the stimulus. It basically just brings up the GUI that I showed you earlier. You can edit subject demographics if you want to enter age and stuff at this point. I'm going to show some of this registration stuff in a bit. You can actually run that same jobs manager to create a full pipeline and run it from entirely within this. Reports, if you happen to have the MATLAB report generator toolbox, which is an extra paid add-on to MATLAB, this will actually let you generate PDF files directly. So you say, generate a data summary report and actually make a PDF where it pastes every single one of the images and all the stats as tables and stuff in it, but it takes a while to run. Just like Homer, we can go and we can click on individual channels if we want to see individual channels. Anything that's been created in the workspace, I can actually go and load up like this so I can actually look. Yeah. Anyway, but I do have a little bit, and down here, if I had multiple subjects or multiple files, this tree would be populated with multiple groups, et cetera, so I can actually navigate through all the different files. Okay. Okay, cool. All right, so let's go back to what I started to show. So this probe field contains all the information about the layout of the probe. And in the case of the NIRx data, because Thomas registered this up when he made the montage, it actually contains all the information for 3D mapping and image reconstruction to actually to do those parts of the toolbox. So based on, it's actually the head circumference and stuff gets read in the mesh that NIRx loaded, which I guess is the Colin 27. I actually take that mesh and I compute head circumference and the arc length and stuff like that. But you can actually adjust this if you actually measured that on an individual subject. But what you can do is this probe has this field called default draw function, which right now the default draw function is 2D. It's drawing all my images as kind of a 2D layout. But what we're going to do is let's change this to the 1020 map. And let's do that same command now. Draw. Come on. Oops. So now I went and I changed the default draw behavior. And so now when I issue the same command of stats.draw, what it's going to do is actually going to draw it in 1020 space. So you see that same map and all that same information about the stats is now presented in a 2D map. And if I look at what other features I could have used, if I do this and add question mark here, it actually tells me all the different options that I had that I could have fed there. And so we're going to use, let's do from the top of the head, so 3D mesh top or 3D mesh superior. And so now if I issue that draw command, there we are, it should draw it in as a 3D head. There we go, and there's deoxyhemoglobin on the top of this Colin 27 head as read by, as imported from the NIRx data, and I said we're going to view it from superior, so we're looking down on the top of the head, but this actually is a 3D object that you can grab and twist and rotate around if you want. Okay. So, any questions at this point? Okay. So we have, again, if you go through the demos that are in there, there's a couple of other features that are kind of cool. Here's .utilities depth map. And what let's do is, so the depth map feature, what it does is based on the Colin 27 atlas, I have all these different labels. And I can take that probe, my location of the probe, and I said pre-central. So I want to look at the precentral gyrus. And so this is a map of, based on column 27, where was the precentral gyrus? And my color scale here is depth. It's depth from the surface of the scalp. So it tells me that my probe, right there, the front part of my probe should be over precentral gyrus. So we did a good job at positioning, where we put this. And the precentral gyrus is, roughly, 15 to 17 millimeters from the surface of the scalp, so within our range. It tells me exactly which source detectors I actually reasonably expected to see, although granted, Thomas is not column 27. So it's, you can figure out who column 27 is based on the authorship of that paper. There's only one column on that paper. Yeah, so this is approximate. If I actually had Thomas's anatomy, we do have advanced ways to actually put his anatomy into this. Though I don't have the labels quite as nice on his brain. We use the free surfer. Free surfer will label some of these regions like precentral gyrus and stuff, and so I can derive that from individual anatomy. We can also, let's see. If I ask for an output here, so I ask for it to return a table, it'll actually return a table. I guess this is the part we want to look at, where it'll tell me for every source detector or source detector pair, which is the midpoint between a source detector, it'll tell me the XYZ coordinate of, I think this is the nearest brain region. So if I just draw a line straight down into the brain, what do I hit in I think these are tau rock coordinates. It'll tell me then the depth of that brain. So if I went from source 5, detector 5, straight down in 21 millimeters, I would hit the brain, and specifically that area would have been that's how far I am from the precentral sulcus. So it goes, and you can actually do this. Actually, what it's doing is it's telling me the distance from this to the precentral sulcus. If I do this with a question mark, it should, after it thinks for a while, it'll actually tell me which brain region was the closest. So here you see source 5, detector 6. If I draw a line straight down into the brain in 19 millimeters, I would hit BA2 on the right side. I would also hit the precentral sulcus on the right side, same location. So it uses both the Brodmann areas and the anatomical folding areas in the atlas. And what we can do from there is we can say ROI equals NIRS dot utilities dots. Actually, this is where I need to pull up my cheat sheet. And of course, I didn't copy this in here. Now let's see if I can figure it out. ROI equals NIRS dot utilities dot, and if I hit tab, it's going to tell me all the different, it's going to try to autocomplete, so it tells me all the different options that were within that utilities. And fortunately, I'm able to find this convert labels to ROI. Oops, convert labels to ROI. So given subject stats dot probe, given that probe, it'll actually automatically generate which regions of interest were underneath my probe and which sensors, what was the relative sensitivity of each of my source detector pairs to that region of interest. It takes a little bit of time on this. My computer's a little slow. Please work. Actually, I know what I'm going to do. Kill that. Sorry about this. I'm going to ask for a specific region rather than letting it choose every possible region. So I'm really, pretty sure I spelled precentral. Precentral. There is no precental sulcus. So it basically tells me what this is this is a list of all my source detector pairs and the relative weight of that source detector pair to the precentral sulcus. So you can really see for the left precentral sulcus, the channels that were closest were source 2 detector 5 and source 1 detector 3 with a little bit more weighting or less weighting towards some of these other ones. And so what I can do is I can actually use that then, so I can say ROI stats is NIRS dot utilities dot ROI average given my subject stats and the ROI definition. And ROI stats now, yes, that's what I meant, this is now the stats variable. So I used, based on the location of my probe relative to the head, I said which sensors were, what was the relative contribution of the precentral sulcus to each sensor. I then ran a region of interest average. And this is now for the two conditions, left and right, and deoxyhemoglobin for my left and right precentral sulcus. This is the statistical, so we see, extremely statistically significant on the left cortex to the right tapping, and hopefully the right cortex to the left tapping. Exactly what we thought we saw. When we run these regions of interest analysis like this, it actually is because my stats model at the first level knew all about the channel by channel, that these two channels were not independent. That's actually taken into account when I do this. So when I average multiple channels together, I'm able to acknowledge the fact that they weren't actually independent measures and correct for it when I do these things. And you see, actually, your power goes way up because you're averaging lots of channels together. Okay, so I wanted to show, so that's, again, kind of, if you go through the toolbox, there's, in those demo folders, there's a lot you can do with playing around with that kind of stuff and NIRx data and so on. I want to show a little bit of group level stuff as well. So I loaded up earlier this morning, I loaded up a set of data that I created that actually has a little bit more interesting features in it. And so in this one, I have there's a total of 12 files that I've loaded. I've ran the first level model. It takes a couple minutes to run. I just didn't want to do it here. But that data, the first data file of those 12, the first one was a patient's group. It was their first visit for subject 1. The file number 2 was patient's group, second visit, subject number 1, so on. So I have a total of 6 subjects representing 2 groups, patients and controls, and each subject came in for 2 visits, okay? So I ran this model out, and if I look at, this is looking at just the first, this is actually kind of simulated data. That's not a great one, but that's this is basically, it's kind of a forehead type probe. It's actually a kind of a weak effect. Actually, if I look at any one subject, I'm marginally making statistical significance, maybe in some of the cases, depending on which file I look at. When I look at the group average, I'm going to have a lot better resolution. In most studies that are not done on Thomas's head during finger tapping, it usually takes a few runs, a few subjects before you actually see effects, right? So this is kind of more standard. But I have this representation, I have this condition A, the task, whatever, that's represented in these different groups. And so what I can do is I can actually run this mixed effects model. So I'm going to create this job by using the mixed effects model. And one of the features in this job is what's called the formula. And so the formula is how I'm going to specify my ANOVA test. Okay? So same as you would in SPSS or so. And any features, that subject, that visit, that group, and the condition are available to me to use in the formula. It supports, it's running a function in MATLAB that's called LME fit, for linear mixed effects model fit, I guess. And there's a whole, it's calling that function, there's a whole slew of ways to specify the formula, including both linear and nonlinear interactions and so on. So anything that I'm using that are in that demographics can actually be called within that formula. But let's set up a condition here that I want to look at. So let's do this one. So what I'm going to do is I'm going to look at the brain activity beta. I want an image for each group, for each condition, and for each visit. So that means I'm going to have 2 groups times 2 visits, and then 1 condition. And I'm going to treat subject as a random variable. So this is the notation, this one in brackets, like 1 vertical line, is how you denote random effects. So I've got a fixed effects term and a random effects term. This -1 means drop off the intercept. It takes a little bit of reading to figure out how to do these formulas, but there's a huge amount of flexibility to specify this. It's what's called Wilkinson's notation. And so if I run this, we're going to say J equals run of, we're going to take that stats variable, which had 12 subjects stored, and we're going to run that model on it. We're saving the result as G. And now if I say G.draw, what I'm going to end up finding is I open up, let's get rid of, let's only show the oxyhemoglobins, otherwise my figure's too big. Now what I did was I actually had basically a demo data that had the same task in every one of the subjects. So I kind of fictitiously added groups and sessions on for the purposes here. Actually, hopefully, I didn't actually look this morning, but if I statistically test group 1 versus group 2, I shouldn't actually find a difference because they actually came from the same subject pool. I just made this up for this demo. But by running that formula, you see I end up with, here we see oxyhemoglobin condition A, the control group for their second visit, for the control group for their first visit, and so on. So I end up with all these different images based on how I set up that formula. And what I can do then is I can take this and I can actually now start to do second level stats. So to look at all the possible conditions, let's do a t-test on So let's do a t-test now. This is, actually, I didn't threshold it. So the expectation is nothing's going to survive this, but I haven't actually looked at it, so it worked, cool. But this is now, so what I did a t-test of, I have all these 4 different conditions. I'm doing a t-test of the control subject's first visit to the control subject's second visit. So this is an image of what parts of the brain were different in the first visit compared to the second visit, and the answer was none of them. I do the same thing, again, kind of using any combination there. I could do, controls visit 1 plus controls visit 2 minus patient's visit 1 and patient's visit 2, and that would be just the average of the 2 conditions, subtracting the groups or any combination thereof to actually do my analysis like that. Is there any questions? I've got like 5 minutes left, so I'm going to stop there and just take questions because that's a good. You were first.
This probably is very basic for those who do this, but I'm at a bit of a loss how you're doing this, averaging and co-registering people without anatomy. So is it comparing probe 1 to probe 1 on everyone?
Yeah.
How does it guarantee that you're all hitting the
it's not. There's the problem of registration across subjects. The best case scenario is you have a structural MRI, you've registered up the probe using a 3D camera or something like that, in which case we can account for all the differences in anatomy and probe placement and so on. In most cases, you don't have that information. So that's kind of the best case scenario. What we did here was we loaded up the data. We assumed that the probe, because it's aligned to 1020 systems, that we put it on the cap in a reproducible way. And we're just and so we're assuming that channel number 1 was over the same anatomy in every subject for what I did here.
So is
If
that
I actually had
recommendation
variability in head size, there actually is, we're working on ways to account for that. If you actually have variability in head size, or something like that. You can do region of interest based. So if you were worried about, okay, maybe it's channel 1 on my head, but if Jonathan's got a smaller head than me and it's maybe channels 1 and 2, you could go, the way that we might conventionally deal with this in the NIRS field is maybe just a region of interest average. So we just take like the channels on the left side and region of interest average them, and then pool the region of interest averages on the group level. There's different ways to go depending on A, what data you have available to you, structural MRI or not, or how well you've registered the probe, and B, kind of what kind of assumptions are you willing to make. So here, with this kind of analysis right now, obviously we don't have structural anatomy, so we're assuming the probe is over the same location in each subject, and we're just averaging all channel 1s together and all channel 2s together. But if you do that analysis, you recognize that that's not entirely accurate, and if I'm doing something like child development where the head's growing or something like that, that's not maybe going to be sufficient to address certain types of questions. But I don't have some of that. If you dig closely enough through my toolbox, there are hints on how I plan to do that, because there are modules that actually do some of that registration and recorrect for head size and stuff, but it's not established yet at all.
So can you register each person to the atlas and take the probes that are closest to
Yeah. So if I had like a head size and I know this was a 54-inch circumference person and this was a 60-inch circumference, I could go and I could register, I could go and run that region of interest code based on the head size, where I say, oh, give me all the channels over precentral sulcus or something. I take that region of interest, and actually you can run these jobs, these t-tests and the mixed effects. You can just feed in the region of interest. You can go from the subject level into a region of interest variable and then run that through the module. What'll come out the other end will be a region of interest stat, but it works the same way. And actually, if you say draw, I think it draws a bar chart instead of a nice picture of the brain. But yeah. You were next.
So, if you have, say, an arbitrary setup of channels, what does that data structure need to look like to be fed in? Could it mimic what the NIRx machine puts out?
So my toolbox inputs, so it's NIRS.io is all the input functions. So I have for Boxy, which is the ISS, the .NIRS, which is the Homer version. So if you can get your data into a Homer version, I can use it. Hitachi, NIRx, the Ardennis, wireless, which is one of the Tekken ones. So if you can get it into one of the formats of the other, kind of a standard format, I can read it in. With some of the ones like the specialized, like the NIRx, where it's loading it directly, I'm taking advantage of like all these extra fields that are in the header files and the event files and stuff like that. But I can just load straight out .NIRS files that Homer would have accepted. I'm hoping that we, in the NIRS community, kind of have finalize some of these discussions of a set NIRS data format. In which case, that'll make that argument a little bit, a little bit easier. So, yeah. But I mean, fundamentally, what you could do is you could just create the variable and just load it up, and write your own load function anyway. So it's not. And if you look, actually, one of the things I said I might, which I will, all of everything I just said I can reproduce for EEG, MEG, and a version of fMRI data called SIFTI files. But all of those, in the toolbox, if you download it, there's a .NIRS folder. There's also a EEG folder and a dense time series folder. And all of the modules and all of the commands and the draws and the stats and stuff are all interchangeable. So you can actually run all functions from my EEG toolbox on NIRS data, sometimes even if it doesn't make sense, because obviously running the Beer-Lambert on EEG doesn't make sense. But a lot of the tools are actually, they use the exact same formats. So we've been expanding now in those contexts. And the reason for that, we still do all of our EEG or MEG in, M&I or these other dedicated toolboxes, but doing it in this format lets me get it into all of my data is in the same structure from the different modalities, and so now I can start to think about multimodal problems and everything I talked about yesterday. Almost all of that can be done within the toolbox at this point with those multimodal methods. So, any other questions? Yeah.
It's not a technical question, but probably it's good maybe to bring it up. About the referencing, do you have any preferences? Because I know not right now.
Oh, for referencing stuff?
Yeah.
Oh, cool. Yeah, that's, I totally forgot to mention that because I added this feature because someone from the NIH yelled at me that I wasn't, if you create a pipeline, you create up your pipeline and you say pipeline, job.cite, it'll actually tell you all the publications to cite that you used in that pipeline. Yeah, I got so yelled at by the NIH because we do some work with the intramural program, and they're like, we paid for this, you need to have us being cited. So I added all those features. Yeah, but at the moment I do not have a publication that specifically describes the toolbox itself, only the methods contained within. Yeah.
So, for example, there are several parameters like you said, the subject could have one and kind of random. So, for those kind of parameters, do you have any document?
Well, I mean, it's running. That's one of those things I need to put in the reference for when I write up the paper for this toolbox. There are a couple of papers that we've explained what we do because we've used the methods, even though we haven't published the toolbox paper yet. It's when you set up the ANOVA or the mixed effects model, what you do to do a whitened or weighted version of it is you take your covariance matrix, you decompose it, and then you multiply both sides of the equation, so there's now a weighted version. And we're able to, because we have all that spatial covariance, the channel by condition covariance from the first level models, when we run the ANOVA, we're actually doing a weighted version that takes that into account. And I can write down all the equations. Actually, the equations, the talk I gave right before lunch where I said there's a bunch of slides that I'm skipping, that has all those equations in it. So I'll share that. That's fine, but it's not really published anywhere yet.